Okay, so basically, if you look at chapter 4, we've covered pretty much all the meat of it already, and so there's actually very little left in the chapter to talk about. So one thing I wanted to say, though, is that so by now we have kind of like this bewildering array of possibilities, both for feature detection and for feature description, right? And so, for example, just to kind of recap, for detectors, we had stuff like Harris was our first thing. Then we talked about basically like, what was the next one? Like Harris-Laplace, which is kind of like the multi-scale Harris. Then we talked about Laplacian of Gaussian. We talked about difference of Gaussian. We talked about, if I were to, instead of using just the circle for the apparent scale of feature, and I instead built that ellipse that was affine covariant, I would call that a Harris-affine feature. And at the end of the last lecture, I talked about these fast corners, the one where you just apply like the decision tree, and that's a really fast detector. And we talked about these maximally stable extremal regions, right? And there are there are even more on top of that, right? So there's lots of possible detectors, and then there's lots of possible descriptors. And so the simplest one, like we talked about, would be like kind of the block of pixels around the feature, which is probably not very good. And then we talked about things like, SIFT was the main one, the SIFT feature. We also referred to some other types of histogram-based feature descriptors, like we touched on these GLOW and DAISY descriptors, right? And each of these guys has, a bunch of parameters, like the number of circles, the radius, So there's kind of like this big array of, how would I choose the right detector and descriptor pair for my application, okay? And, I'm not going to lie to you. A lot of people will just say, okay, I know about SIFT, so I'm going to use SIFT, right? But there have been a bunch of people who have done some more systematic studies of what good detector-descriptor pairs are for certain applications, okay? So I just want to say just like a few words about how that kind of evaluation process works. So basically the topic of today's lecture is more or less like feature evaluation, like how good are my features, and then also a little bit heading towards how features are used, okay? So the main thing that we care about for a feature is what I would say repeatability. And all that means is, I pick out so I take a picture of a scene, I pick out a feature at a particular image location, I look at the 3D point that corresponds to, and now I take some more pictures of that scene, and I ask, okay, so I know where that 3D point, so this is the tricky part is, if I know where that 3D point appears in my other images of the scene, did I also find a feature at that image location? So it's kind of like saying, okay, here is my image 1, I found a feature here, right? I take my camera location, I project that feature out into 3D space, I say, oh, it hit this object over here. And now I have another image of the same scene and another camera. And so then I kind of project this back onto this image and I say, was there a feature detected kind of somewhere here, right? Maybe I give myself a little bit of a radius to be sure, right? And so all I'm doing is I'm saying, okay, well, if there's a feature that was detected sufficiently close to that, to where it should be, then I call that a repeated detection, right? If I've got a feature that I can find in one image, but then I can never find it again in any other image of the same scene, well, that's not a very useful feature, right? And so that's why, certainly stuff like, if I were to pick a feature on a blank wall, right, and then I was to try and find that feature again in some other scene, well, I probably would never find another feature that was exactly where it should be, right? And if I did, it would probably be by coincidence and not by design, right? And so I can basically make a repeatability score that says, I look at the number of repeated features I have over the kind of smaller of how many features I've detected in each of the images, right? So things would be great if, for example, say I had 200 features over here and 150 features over here, and then I found that all 150 of these matched up with some of these features over here, well, then that would be very repeatable, right? That would mean that, you know, I'd have a score very close to 1, right? The tricky part is, you know, how do you actually, well, okay, let me say one more thing before I talk about the tricky part. The other thing is that, you know, in addition to wanting to match the feature location, right, to be useful as a matching device, I probably also want to make sure that if there's a detected scale, that comes along and is the right thing, and then there's a detected, you know, even better would be if I do these affine features where I draw the ellipse around the feature. You know, it would be better to say, okay, you know, instead, let's say this guy was detected with this ellipse here. I can kind of project, instead of a circle, I can kind of project what that ellipse should look like over here, and then I can ask myself, you know, for this guy, if I detected him with some other ellipse, do those ellipses have, you know, sufficient overlap, right? If one ellipse is a lot bigger than the other, or if it's oriented differently, then even though the positions may match up, I probably would not call that a good detection, because I probably wouldn't be able to match it later, right? So, you know, the main tricky part is to do this kind of repeatability. I need to know where the I need to know that this and this correspond to the same 3D feature, right? And so that's what makes evaluation a little bit of a pain, is that you need to have a very controlled set of scenes and images. And so one of the easiest ways to do this evaluation is to take a picture of a textured planar object, something like, you know, the canonical one you see in all these feature papers is this graffiti-covered wall, right? And I saw you had this in your homework, right? So basically, you take a picture of this graffiti-covered wall. There's lots of corners and blobs and stuff like that. And it turns out, as we'll talk about probably next week, that I know I can mathematically figure out, if I see the wall from different perspectives, I can relate, I can project all the features from one image exactly into the other image by estimating what's called a projective transformation. So that means that if I, you know, have a planar surface, I can really tell, okay, that's where this feature should be in this other image, right? And so much of the early detector descriptor evaluation was based on taking images of stuff like this graffiti-covered wall. And then later, as people started to, you know, but that's not a very good proxy for some of the problems that we care about in real life. In real life, we care about scenes like this classroom, right, with, you know, lots of 3D variation and so on. And so then people started to build, you know, data sets where they had basically a controlled 3D scene where they could understand where that 3D scene should project down into the images. And so you'll see that the early evaluation papers are on planar surfaces and the later ones are on more realistic scenes. So this score here kind of speaks mostly to how good the detector is, right? Can I find that feature again? This doesn't really say anything about description. It just says about whether I can reliably redetect the feature, right? The other important thing is basically kind of like, you know, what I would call matchability, right? So that basically says, you know, score is something like number of features matched over, again, the number of features I have, right? So this looks, you're saying like, well, what is the difference between this and the thing before? The difference is that here, when I say matched, the implication is that I'm using a particular descriptor and I'm using a particular method for comparing descriptors, right? So this is like saying, okay, I'm going to use SIFT with, you know, my nearest neighbor distance ratio matching, right? And if that distance ratio is above a threshold, I'm going to declare a match. So it could be that in this case, you know, maybe all these features are super repeatable in the sense that, you know, that features were actually detected in the right places. That doesn't matter to me if my descriptor is not good enough to actually make the connection between those points, right? So some subset of these 150 matched features is actually going to be matched, or some subset of these 150 kind of possible detections is going to be actually matched by the descriptor. And so my descriptor performance is usually going to be, you know, a much lower fraction of maybe what hypothetically could be detected. And so the other thing that you see a lot is, you know, there are typical metrics for machine learning, things like precision. So precision is basically the number of correct matches over the number of total matches. Right? So this is saying, okay, you know, if you generated 200 total matches, but then in the ground truth of them, only 80 of them were correct, then that has low precision, right? That means that you have lots of false alarms, right? And that's false alarms are bad because they obscure the thing that you're really trying to estimate. And the other one is called recall, which is the number of correct matches over kind of the number of what I would call true correspondences. And by that I mean, okay, you know, suppose that I know, kind of from my previous slide, that I had 150 potential matches, right? And my detector found 10 total matches. And maybe even if all those 10 total matches were correct, the fact that it only found 10 out of 150 total possible ones means it's not very good, right? So you typically see these curves of precision and recall, right? And obviously I want both of these things to be high for the descriptor to be good. Okay. So any questions about kind of the big picture? So in some sense, you know, you can read in the book about kind of my summary of kind of what the conclusions about these detector and descriptor pairs were. So basically, you know, these studies kind of say, okay, you know, so now I have all these possibilities in column A, all these possibilities in column B, and I can start to kind of hook these things together, and I can see, you know, what combination of this, you know, A times B column gives me good performance for different data sets and different problems. And so, you know, people were using SIFT for, you know, for quite a while before they started to really do this validation. But one thing that was nice is that SIFT did generally come out pretty well in all these tests in terms of the quality of the descriptor, along with the DOG features as being pretty good. You know, in some sense, it's, I don't want to say it's too bad, but like, you know, some features like this maximally stable extreme origin, this detector actually turns out to be pretty good in some cases. And then you could couple that, for example, with a SIFT descriptor, and it would also be pretty good. You know, the sad fact is I'm not sure how many people actually use the results of these, you know, studies to further guide the development of their algorithm. I mean, I'm sure that people who really, really, really care about feature matching will do that, but, you know, if you're just kind of casual computer vision graduate student, you're probably just going to take SIFT off the shelf and use it, right? But, you know, it is important, I think, to do this study. I mean, one thing especially, like I was saying here, for this DAISY descriptor is, you know, there's lots of choices to make, and it turns out that that DAISY descriptor performs really, really well, and you just have to be able to, you know, have some guided choices about, you know, how big should the regions be, how many radii of the circle should you have, how many dimensions of PCA should you do. I mean, there are lots of choices to make that may make the raw DAISY descriptor seem a little bit off-putting to somebody who just has this canned SIFT library. But, you know, if you really care about getting great, you know, great matches, then it may be worth your time to do that. So, so hopefully, at least now you know that there's more to the world than just SIFT, right? Okay, so I'm not going to say too much more about the whole feature detection process, other than to say that, you know, it's kind of weird that, like in this chapter, pretty much every image I showed you was a grayscale image, right? And in fact, you know, most feature detection and description lives in the grayscale world, which is kind of surprising because you'd think that there would be a lot of color information that you could extract and use as the basis for a feature, right? So I mean, you could certainly do, so let me just say, you know, color is the main extension that people have thought about a little bit. You could do something naive, which is basically to say, okay, I'm going to do like SIFT on the, I'm going to take a color image, I'm going to do separate detection on the RGB channels, I'm going to collect all those as possible places, then I'm going to make a SIFT descriptor that is basically the concatenation of the descriptor applied to each of the RGB channels independently, something like that. I mean, that would be a very clumsy way of doing it, but you could do it that way. I mean, the smarter way of doing it is to basically really take the color into account when you're building these histograms. But again, I think it's probably fair to say that a lot of people are not doing that. You know, which is, and maybe part of it is that the SIF descriptor, for many purposes, performs pretty well as it is, without having to go to the extra mile of having to incorporate the color. But, again, I think that's kind of worth thinking about. And so then there's a short section here on how do you take some of these ideas we talked about and extend them into color. Just in the same way, there's like, you could take the idea from Harris corners about what makes a good Harris corner, right, and extend that to color. So instead of having like this notion that as I move around in X, Y, we have this kind of function, that bowl shape that says we want there to be, a nice sharp minimum at the bottom in that bowl. You can extend that idea when you're doing the correlation in 3 dimensions instead of just in one color channel, right? And so people have done that in terms of like color Harris corner extraction. Okay, so the last thing I want to talk about in this context is what I would call artificial features. And so what I mean by that is, so I guess these are my pictures that I forgot to show you. So this is the picture of basically repeatability that I drew by hand. So this is what I mean by artificial features, right? So you guys are probably definitely used to seeing what are called QR codes like this, right? You see them on movie posters and products and stuff like that. And so, what is a QR code good for, right? You take your cell phone, you put it up to the QR code, and your cell phone detects and reads that image, and that image encodes some information. So you might say, oh, well, what I should do if I'm on a movie set and I want to detect features is instead of putting these masking tape crosses on the wall, which, every masking tape cross basically looks the same as every other one, well, why don't I just smack up a bunch of QR codes on the wall, right? And each of these QR codes could encode information like, left, right wall, stuff like, or left, back wall, right? You could imagine that you could do a lot of stuff with individually addressable features. Part of the problem with that is that, QR codes are not built for, QR codes specifically are not built for that application. Like if you were to take a picture of a QR code from across the room, it would look like nothing, right? There's just too much, these pixels are too small, and so even if you look at the kind of larger, there are QR codes where the pixels are bigger, but none of them are going to be citable across the room, right? And also none of them are going to be kind of designed for that purpose, right? So for example, if I was to obscure chunks of the QR code, it's probably not very robust to occlusion, right? But this is not to say that these things don't have their place. Like every Amazon UPS package that you get has some sort of digital code, either a 1D barcode or some sort of 2D fancy code that encodes information. So the next possibility is something called, these are what I would call AR, artificial reality markers. So there was a idea called AR toolkit, and so this is really nothing more than, and this wasn't really invented by computer vision people. This was really more by like cognitive scientists. So the idea was you take a black box and you put a white box inside of it, and you put some other thing inside the box. Could be a American letter or a Japanese character, and then what I can do is, if I take different images of the scene, I can try and find these solid black borders, maybe just by thresholding the scene or something like that, and then I can find these white rectangles, and I can kind of try and unskew them to be square, and then I can try and recognize what's inside the box just by like matching a library of letters to the thing that I detected, right? And so, again, this works okay. Part of the problem here is that there's really, when people made these AR toolkit markers, there's really no attempt to try and make these interior markings, letters, as detectable or distinguishable as possible, right? But then computer vision people started to get into the game and say, okay, well, let's start from what we want to do, right? It would be great if we had a marker that you could extract an unambiguous ID from, right? So I want to have recognition of this is marker number 1, this is marker number 2. I want to have something that is going to be robust to being at different distances from the camera. I want to have something that could suffer from being covered up a little bit, so there's got to be some sort of error correction capability. I want to be able to detect it, in different illuminations and so on. And so that led to these kinds of what I call binary tags. And so this on the right-hand side is actually something, this paper I liked a lot. They're called R tags, AR tags. And so these are really designed very specifically for the, kind of recognition and tracking problems. And I'll show you a video in just a second. So basically what you have here is, again, you've got a black boundary and you've got a 6x6 pattern of binary pixels inside there. And let me just show you a video, if I have it queued up, of rtag in action here. So here, these are some stills from the video. So you can see that what you're going to see is basically, well, let me actually show you the video. Why don't I just say that? And there's probably some way to make this bigger. How do I make this bigger this is clearly like an old video, so I'm not sure how to do it. Double tap, yes, okay. And so here you can see that as the camera moves around, it's seeing these tags, and then it is using them as a basis for estimating where the camera is. We're going to talk about exactly this problem in Chapter 6. This is basically like the match moving problem. And so the idea was that the detection and location of these markers can be pretty robustly done, even on something like a cell phone or an iPad. You don't need a whole computer and all this stuff to do that. So there are different sorts of, like, the idea would be, maybe here's a guy holding his augmented reality tablet, so that he sees a table full of empty markers with his eyes, but through the tablet he sees this, where he can move around and perceive the scene, right? And maybe some of you remember there were some like card game, like Magic the Gathering kind of card games, and even some video games that had some interfaces like this, where there was a tag and you could see like your character perched on top of the tag if you looked at it through the glasses. And so here, you can kind of watch this video a little bit further to see a bunch of applications. Let's see if there's anything kind of, multiple people working on the thing can basically see the right thing from their perspective. And I think this is, so here's an example of the robustness of these markers to occlusion, right? So this, I believe, is an experiment where, if we get past this caption here, right? So here, you can kind of see the numbers of the markers as they get detected, right? So when the guy's hand is over, the full marker, you don't see any, but there's enough markers in the scene that can be detected that it's quite robust to this. And so here there's some more pictures of, so here are people with their AR-tagged body armor who are looking at the scene, and you can imagine following along with some animated character. This person has some artificial reality bunny ears on her helmet, apparently. And so, these I think are really good. And let me actually show you also. So we're using something similar. I guess I should have just stayed in Explorer. So here's a project going on at RPI where we have this dual-armed robot in our lab, and we have a box or another object that is basically instrumented with, these are not R tags, but they're similar. These are called VTT tags. And so, or Alvar tags. And so now the robot has two cameras that are mounted on its forearms, and what it's doing is it's trying to center the middle tag so it knows how to push in with its arms and pick the box up. And so, I don't have the video that shows what the robot cameras are seeing. There's a video like that somewhere. But basically, these cameras on the left and right are being positioned so that they're bringing that tag into alignment for grasping, right? And so again, we're definitely interested in moving on from these artificial tags to, non-tagged objects, right? Where we don't have to do any sort of tagging. But when you've got a constrained lab environment, you can afford to slap some tags on something. You might as well. It's pretty good. Unfortunately, since I wrote the book, and even I think actually before I wrote the book, these R tags, the R tag library that I really liked, apparently is no longer supported. It was done by the National Research Council of Canada, and apparently that project got terminated or something. So unfortunately, you can no longer use the explicit R tags, although the papers survive that kind of tell you how you can implement them yourself, more or less. So let's see what else I have stored here. Oh, here's another example from our lab of basically this is one of Dr. Wen's master's students who used tag blocks to play Jenga, basically. So this robot is looking for tags. When it finds the tag, or looking for tags, when it finds the tag, right now it's actually kind of doing a survey of the environment. It finds something that it likes. It kind of swivels in, focuses on it, picks up the block, and then it stacks these blocks, right? So actually it's more like a block stacking robot that is a Jenga playing robot, which is the other way around. But this is like the first step to Jenga playing, is understanding how to stack the blocks. And here this is just a connect interface to guiding the robot to the block, and the robot uses the R tags to swoop in and pick up the block, right? So definitely in things like robotics and so on, these artificial tags make a lot of sense, right? So it's definitely, if you're doing a project like that, it's definitely worth thinking about, could I save myself some time by putting a couple binary markers on things instead of just letting SIFT features or something like that do all the work? Oops, no, I don't want whoever this is.
They were controlling you with the connect?
Yes, yeah. And I can show you. I'll show you some more stuff like that when we get to the connect section. Okay, so let me just say, in the context of visual effects, though, I think it's fair to say that you don't see these binary tags used a lot, and part of the reason for that is that a movie set is an incredibly stressful environment. Especially for the visual effects guys, because basically so much of the time in getting a shot has to do with, there's all sorts of considerations. You have to set up the camera angles, you have to get the lighting right, you have to get all the practical effects and stuff like that right. And so, they don't want the visual effects guys taking half an hour or even 15 minutes to kind of put up all these, specially tagged markers, especially because, there's an attitude of we can just kind of do anything in post-production, right? And so, in some sense, even if you say, oh, look, if you just gave me 10 minutes, I would save you $400,000 in post-production costs. I don't think that calculus applies when you're actually on the movie set, right? So, when I was talking to the people who actually do this for a living, they were saying that, yeah, all your computer vision ideas about how to do feature detection, that's great, but I mean, we don't do that in the real world just because it's not practical for us to do so. I mean, what they may do is, in the sense of an artificial tag, what they may do is they have like a little kind of like what they call it was a teepee, right? So they have a little bag with rods and sticks that they can build like a little pyramid thing like this. Like you can imagine, you pull out a bag, you assemble it, you put it in the set, and that gives you, number one, some features. You know where the what the corners of this thing should be, and you also know what the geometry of this thing should be, so you know what the shape of it is, and that gives you some quick sense of scale, and it gives you at least like 7 or 8 feature points. And also they have like little cubes that they can put on the set, quickly put them in and out. The other thing to think about from the perspective of visual effects is that there aren't as many problems where you really care about the situation that SIFT was designed to solve, right? So you might say, oh, everyone in Vision uses SIFT features, right? So don't you guys in visual effects use SIFT features all the time? And the answer is no, because they don't really have SIFT problems that often, right? So the problem that they have most commonly is camera tracking, where you've got a camera and the camera is moving through the scene and you want to use that to do basically like 3D camera motion estimation. We'll talk about that extensively in a couple of weeks. But for that, you can get away more or less with just tracking Harris corners, because the scale of the scene is not changing from image to image very much. You don't need all the fancy stuff about affine invariance and stuff like that. You don't need a fancy descriptor. All you have to do is match blocks of pixels. And presumably, you're moving through such a feature-rich environment that if your Harris corners get lost, you just bring new ones in. So basically, there's not like this need to track every feature, right? So as long as you've got enough to do a good camera track, that's what matters. Although, I think that's, that being said, I think that there are definitely places where SIFT could help you a lot. And so one place, for example, is in this match moving problem, you suffer constantly from what I would call broken tracks. So the idea being that, I have a, I would say I'm tracking this piece of background, and then in the next scene, this guy walks in front of it, so the feature is gone, and then by the time you see the feature again, the camera is moved and it's over here, right? So maybe, it would be very difficult for just basically block to block, normalized cross correlation to find these two matches, because maybe here this is a square, and over here this is a, skewed, the region is now a skewed, rectangle. So this is a case where SIFT could help you, right? It could help you hook up this to this without thinking that, this and this were totally different tracks. And knowing that will help you a lot, well, not a lot, but it will definitely help you in the 3D reconstruction problem, right? So instead of having a bunch of small broken tracks, maybe you can connect those up into longer tracks that you know belong to the same 3D point, right? So that's something that, again, could potentially help you by using a better descriptor like the SIF descriptor. Okay, so let me just also go back to kind of real-world features. So that's pretty much all I can say about features for visual effects. But features for, so let me just, here are some pictures of features that you would see in visual effects before I stop. So here, this is very common. You got a green screen, you throw up some masking tape crosses, you use some sort of Harris-like corner detector to find where those things are, and then you use the apparent motion of those features to put the 3D background in a way that looks realistic. We didn't talk about that problem yet, but we will. Again, here's another case where they've put up, again, when people are doing this, there's probably not a lot of rhyme or reason on the set to, it's not like this pattern of features I don't think was very planned. I think that probably what they were trying to do was just say, okay, to make it a little bit harder. So in this case here, all the pluses look basically the same. Here you say, okay, well, I'm going to try and not put two pluses next to each other in the hopes of not having to confuse two things, right? Here's a case where this is, again, a blue screen environment, and instead of pluses or crosses, they've chosen to use these triangles. And so they're kind of small, but you can kind of see that some of these triangles are pointing down, some of them are pointing up. That's what they chose to use on this. Here's a still from Thor. I was just watching this last night, actually. So again, here they've got, again, red crosses on a green background in an attempt to make this stand out. So again, if you're doing anything in a natural environment, you're going to have to deal with natural features. And so, again, pretty much any shot in a real-world thing is using, maybe something like Harris corners. So here's just a sketch of a scene from the second Transformers movie where, I kind of sketched out what would some of these tracked Harris corners maybe look like in this scene, right? You're latching onto things like corners and intersections and blobs and stuff like that. And again, for anything like this, like an aerial shot, you probably, again, would be detecting things like, now that I showed this on the first day of class, but now you can kind of think about, okay, so looking at this, you could think, okay, imagine that the windows of these boats and the white blob of the bus on the dark background, stuff like that, are probably going to get picked up as features at different scales. And then again, this is Black Swan. You can see that these features, these dark blobs on the light shoulder background, are probably going to be picked up very easily by something like Harris or something like a blob detector, right? So this is exactly what something like a Laplacian Gaussian detector is good at, is finding blobs, right? Dark things on a white surround. And here, this is really a combination of all sorts of features, right? So here, this guy has got, kind of small scale blobs on his face, and he's got, the white and black circles. Again, you probably find those with a Laplacian type detector. And then these Sierpinski triangles, I think, this is a proprietary bodysuit made by ILM. And so I kind of be curious to know whether or not they're doing, actually detecting the corners of these triangles at different scales and using that for tracking body reference, or whether they're just using the paper tags and using those. I mean, they actually won an Oscar for this IMOCAP system, and so I would be curious to know what's under the hood of this. But then again, this is basically like, the closest that you get to like artificial features on the set is these types of, paper bands around this person. But in your world, in our world, in the real world, so one thing that just came out a couple weeks ago, I don't know why I have this on here, this is not what I want. Yes, so have any of you guys seen this Amazon Flow? This is really impressive. So this is an app you can get for your phone, and so basically what's happening here is that your phone is doing real-time feature detection, okay, and it's sending those features up to Amazon, and Amazon has a library of features it's extracted from products, and it matches you with the product like almost instantaneously. So like this guy is like walking along a bookstore window, and as he walks past it, his phone is like, you can see, identifying on the bottom all the products he's walking past. And it gives him an immediate Amazon link to, do you want to buy this thing? It's actually pretty scary. This is the kind of thing that would put the independent bookstore out of business, because you can do the one-click find it, right? And again, I don't know that you can see it on the screen, but I have it on my phone, so I'll show you in a second. But it actually, so he's making a shopping list of like, you can see kind of, if you pause. So here, see these white dots, these are features, right? These are basically like Harris corners that are being detected. You can see they're being detected at the corners of this dark thing in the background and on the, on the corners of these letters and stuff like that. So, I mean, it's not hard to put together the feature detection on your phone to find these features in real time. And then to do the matching, this is what I would kind of call, so I didn't talk at all about like how you use features for object recognition. But really, I mean, what it comes down to is you have a set of features that you found in your current image, and you have a library of other features. And so most commonly, this is what I would call you hear sometimes called a bag of features or a bag of words model, where basically you represent an object not by its shape and color and stuff like that. You just say, okay, here are all the features I detected, and I'm kind of looking at like a dictionary of how often I see these features when I see images of that same object. So you can use bag of words models for detecting all sorts of stuff, right? And so I suspect that's what's going on here. Another thing that maybe you may have seen is Project Tango from Google. Anyone see this? So basically, this is a smartphone that is doing 3D navigation. So this guy, Johnny Lee, he did all sorts of really cool stuff. So I have to wait for a second while these guys, so lots of people were involved in this project, many smart people in a busy lab. And so here what you're going to see is they have basically built this custom Android phone. And again, here, hold on a second, I went too fast. So here you can see that this phone is again detecting real-time features that's moving around. I mean, this I think is because it's mounted on this weird robot arm that's gyrating about. But you can find these green dots are automatically detected feature points. Again, probably I would guess they're more like corners, maybe multi-scale corners, maybe not. And it's also hard to tell whether or not there's some sort of like secret sauce built into. I think there's also some innate 3D sensing on this device. Hey, what happened to you? But now, on the basis of these features, the phone is actually able to localize itself in 3D. And so this is like someone doing 3D mapping of an environment as they're moving around. And again, all this basically starts from features. Now this thing here, when you see this video, I'm not sure this is done with features. I think this is maybe done more with, I would say, some sort of, well, I don't know what's under the hood of this. And then they're being a little bit cagey about what 3D technology is in here.
What they just showed made it look like they might have, it might be almost like a prime sense sensor.
Yes, so here it says integrated depth sensing, right? So that makes me think that this is not just a single, normal camera. I mean, it does have other stuff, like this motion tracking camera is probably the one that you saw where it's finding the green dots and figuring out where it is. But this integrated depth sensing is the question mark about exactly what is in there. Is it like the prime sense,
Yeah, it's probably shooting infrared into the scene.
Yeah, so that's a good question. So, I mean, and this is just the first prototype video that anyone ever saw. This a couple weeks ago, and so until people start to get the developer kits and see what's actually under the hood, it's hard to know what we're seeing. But again, the fact that your phone now, and of course, it's also not clear to me whether or not the phone is communicating stuff back to the mothership or internet, or whether it's actually doing all this stuff on the phone. If it did it like totally on the phone, I mean, this is really crazy to imagine that your phone in a couple of years could basically do 3D mapping. And so this thing where we're building up a 3D set of points as you move the phone around, that I think is a kind of a form of what I would call multi-view stereo, although this maybe is not done with the same modality. We'll talk about that in Chapter 8, different methods of acquiring 3D. And so, but again, this is like, between this and the Amazon Flow, these are kind of two great examples of computer vision stuff coming into the consumer mainstream. And so it's kind of a cool time to be seeing this stuff. Okay, so I think that's all I want to say about features. Are there any questions about features? Okay, so what I'm going to do is I'm going to stop the recording, and I'm going to